In this video, I'm going to be working AP Pre-Cal Homework 11-4 and doing some example problems on semi-log plots, specifically graphing exponential functions on a semi-log plot where the y-axis has been scaled logarithmically. That's why it's a semi-log plot. Only the y-axis is logarithmic, the x-axis is just kind of regular. All right, so plot the following points on the same coordinate plane. Yes, that's exactly what we should start with. All right, so A, 10 and 2,000. Okay, 10 to the 3 is 1,000. I think I'm going to point these things out. 1,000, 10,000. 10 to the 2 is 100. 10 to the 1 is 10. And 10 to the 0 is going to be 1. All right. So when I'm going and looking for, say, the point 2,000, okay, the point 1,000 is, or the height of 1,000 is right there. But then that next line up, that means 2,000. We did this a little bit in the lesson. 22 and 250. Okay, okay, looks like each of the tick marks on the x-axis is going to be 2. So 22 here, and then 250 would be, okay, 100. The next bar is 200. Halfway between that bar and the next one, that would be 250, I think. Now, it's probably not halfway, now that I think about it, because half is not, exactly what we think it is on a semi-log plot. But, in the middle, in between those two lines, that's going to be good enough. 30 and 1, okay, 1 is 10 to the 0, that's going to be down there. 38 and 17. Okay, well, all right, 10 is up here, 38. 20 is the next line, so maybe it's just like really close to 20 right there. And then 46, 5,000. Okay, so 46 is going to be 3 ticks over from 40 up to 1,000, 2,000, 3,000, 4,000, 5,000. Okay, that's my best sketch. Okay, that's maybe plotted some points. Okay, we've got points A, B, and C plotted on the semi-log plot where the vertical axis has been logarithmically scaled. We're going to answer the following questions. All right, coordinates of point A. Well, x is definitely 1, so that will help me eliminate one of the answer choices, right? E is out. Okay, the y coordinate of A, okay, 100, 200 is going to be 300, so it should be 1 and 300, yeah. Okay. Then the coordinates of point B are most likely going to be, okay, well, x is 2. Okay, so we'll get rid of that. And then y is going to be 10, 20, 30, 40, 50. I'm just going to have to go ahead and say that's 50. So that's the output I would expect there. Then coordinates of point C. X is definitely 4, so we're going to get rid of that answer choice. And y is going to be halfway between 10 and 20, or somewhere between 10 and 20. How am I supposed to know whether it's 15 versus 16.6? Let me think about that for a second. Let's see. I'm going to have to pause this. All right, so this is the best I can figure. Okay, definitely I know that 10.5, that's too good to be true. That'd be really close to 10 on the scale of 10 to 20. So that one's out. Don't like that. I also don't like 66. That's not even close. I know it's between 10 and 20. But I'm noticing that on the semi-log scale, halfway is actually looks like more like 3/4 of the way. So if this point C, it does look like it's a little bit more than halfway between 10 and 20. But it's definitely, it's at most 3/4 of the way up there. 16.6 would be even closer to 20. So I am pretty confident in saying that it's most likely going to be 4 and 15. But that's a bit of a stretch, I think. I'm just going to move on. Hey, this table is really blurry. Table gives selected values of the function g. Which of these graphs could represent these data in a semi-log plot where the vertical axis is logarithmically scaled? All right, so I'm looking at the table, and the first thing I'm noticing here is that the output values are multiplying by 3 each time. Yeah, that seems valid. 800 times 3 is definitely 2,400, and then 10 times 3 is 30, yeah. Okay, when the x's are evenly spaced, 10, 20, 30, 40, 50, they're just increasing by 10 each time. So this is an exponential function. So that's what I'm going to say. G is exponential. which means that its graph on a semi-log plot needs to make a line. Okay, now let's see. This is not a line, nor is it a semi-log plot. And that's also what I'd say about D. This is not even a semi-log plot, so it's out, right? I'm not really going to be considering that one. So now I got these two. And now, okay, we had one like this in the notes also, where we're thinking about the output values. Okay, the largest output value I'm seeing is 2,430, which is a whole lot more than 10. So, oh, maybe that, okay, maybe B, yeah, B is a semi-log plot. It's just 1 to 10. But this is going 1 to 10. This is not 2,430. I don't see it. That's going to be here. And I know that this would be 2,430 because that is 2,000. And then the next line right there is 3,000. Okay, so it's between 2 and 3,000. That makes a lot of sense. Let's keep going. Okay, using the same data from the question above, so the same g of x table, write the equation of the exponential function that models the data. Okay, if I've got it enough, and I don't want to pull out the calculator because it's pretty painstaking to click on the buttons for the videos, at least on my computer. And I'm going to just solve this one algebraically. So I know that the constant multiplier is 3. Okay, so we know that we're going for y equals a times b to the x. Okay. You know, we could just plug in 2 points and solve the system the way we used to. I don't think that's going to be the way to go. B is going to be, oh, it's going to end up being the 10th root of 3. Let me think about what I should do for that. We're going to run a regression. Okay, so I get the calculator out. You've seen me do this before. I'm going to edit the list. 10, 20, 30, 40, 50. I think that'll work, yeah. And then 30, 90, 270, 810, and 2,430. All right, then we're going to stat calculate an exponential regression, okay, option 0. And who knows what, I saw there's another part of this question. I don't know what they're going to ask me to do, so just in case I need it, I'm going to store that regression equation into y1. There we go. All right, so A is 10, and that does make a lot of sense because the previous entry should be 0 and 10, because I should go to the left by 10, and then divide the output by 3. Yeah, so A is equal to 10 times 1.116 to the x. You might be like, wait, I thought I was multiplying by 3 each time. I'm going to just write out the equation first, and then I'll explain what this 1.116 is. G of x equals 10 times 1.116 to the x. Okay. And I was going to say, okay, yeah, what's going on here, if you were to solve this one algebraically, I'm going to actually show you what would happen. Okay, 10, 30, 20, 90. So 20 is going to equal a times b to the 10, and 90 equals a times b to the 20. So I take the second equation and divide it by the first, and I would get 90 over, wait, 20, that wasn't right. 30, right? Yeah. I'm supposed to get 3, because that was the whole thing with the common ratio. If I take the second equation and divide it by the first equation, I'm going to get 90 over 30 is 3, equals a divided by a is 1, b to the 20 divided by b to the 10 is going to be b to the 10, so b is going to equal the cube root of 3. And then you could, you know, not the cube root, the 10th root. Okay, I didn't change that. Okay, and then I'm going to just verify that with a calculator. I'm going to go over here to the main menu. And I'm going to just take 3 to the power of, you know, 1/10, right, rather than the nth root. I mean, I'm sure there's a command for that in the calculator, but that's where we get that 1.116 number. Okay, that's good. I'll get rid of that. And okay, using the same data from the question above, write the equation of the logarithmically scaled function shown in the form log of y and also log base 3 of y. And when we say log without a base, we are implying base 10, which does kind of make a lot of sense because, you know, it seems like we're always sketching on these semi-log plots where the log has base 10. All right, anyway, I've got y, or g of x, I'll just call it y for now. Y equals 10 times, call it 3 to the 1/10 to the x. Yeah, that's what I'm going to do. And then I'm going to take the log of both sides. And then that is a 10 multiplied by 3 to the 1/10 of x. Okay, and then I'm going to be saying, all right, well, that'll be log of y. I could probably make that look like it's the argument, not the base. We're going to split over this multiplication right here. That can turn into a plus. And then mx plus b. So log of 10, that's going to be 1, right? What exponent do I put on 10 to get 10? Plus base 10 log of 3 to the 1/10 x. But remember, we've got that power property as well, where we can swing that thing around the front. And that will leave me with something like, so I'm going to try to squeeze it in, log of y equals, okay, swing the x around the front, or maybe I'll hold it off until the end, the log of 3 to the 1/10, and you could call that 1.116, or you could call it 1/10 of the base 10 log of 3. You could use the property again. We just said mx plus b, so mx, still adding, whoops, log of 10, which is going to be 1. I'm just going to leave that there. Okay, I could also do the same thing, taking a base 3 log, so log base 3 of y is going to equal log base 3 of 10 plus, I'm just, we did all of this work earlier, and it's going to work out the exact same because the log properties don't depend on the base, right? So that's 3 to the 1/10 x. Oh, so, all right, I kind of see something. I see what's going on here. And so that's log base 3 of y equals m is going to be log base 3 of 3 to the 1/10. Well, that happens to be 1/10, right? What exponent do I put on 3 to get 3 to the 1/10? I put the 1/10 exponent on it. Times x, and I might give a little more detail on that in a second, plus log base 3 of 10. Yeah, I wrote that backwards, but log base 3 of 10. All right, yeah, let me move this down a little bit and be a little bit more explicit about what happened with that. Log base 3 of 3 to the 1/10 x. I think first I would do the same thing and be like, all right, I'm going to deal with this x off to the side. And then I'd be multiplying by log base 3 of 3 to the 1/10. Remember, log and exponential, they undo each other. So log the exponent I put on 3 to get 3 to the 1/10 is 1/10, and that's why I have 1/10 of x. So that goes here, and then that became there. And just to write it as mx plus b, where m and x come before b, it looked like that. All right, there we go. Explain why the data set is exponential. Then write an equation for the exponential data set in the form y equals a times b to the x, and then write the equation of the same data set on a semi-log scale in the form, in the same form that we're used to. All right, great. So what we're going to do is we're going to explain why it's exponential. Well, the x's are evenly spaced. Might say delta x is constant. If you wanted to be specific, it's constantly 1, right? Because each time you move over to the next entry in the table, x is increased by 1. Okay, it must be that 6 over 5 is the constant, proportion. I'm going to say, okay, 6 divided by 5 is 1.2. I know that. I'm going on the calculator. I don't think you need to see me do this. 6 times 1.2, I know 6 times 12 is 72. That makes a lot of sense to me. I'm going to do 7.2 times 1.2 just to make sure I get 8.64. Yeah, okay. Delta x is constantly 1. Output values have a constant ratio of 1.2. Okay, so that's why it's exponential. Then we're going to write an equation for the data set. Well, I just found that the multiplier was 1.2. All of those times 1.2. And so it's going to be y equals a times 1.2 to the x, because that's what that 1.2 does. It's the base of the exponential. It's kind of the growth factor. Now, if we wanted to figure out what a is, Okay, it is the output value at x equals 0, but you know, you can just plug in a point. I am going to choose x equals 0. When x equals 0, y equals 5, 5 equals a times 1.2 to the 0 power. 1.2 to the 0 power is 1, so 5 equals a. So y equals 5 times 1.2 to the x. And then they're going to want me to write this with the log situation. So I'm going to take the base 10 log of both sides. Okay, I'm going to first split over the multiplication, turn that into addition. And maybe because I know how this is going, I've done it a couple of times, I'm going to say that's log of 1.2 to the x plus log of 5. And we don't know of a special exponent that we can put on 10 to get 5. It looks appealing because 5 is half of 10, but there's not anything for that. And so that's going to be log base 10 of y equaling log base 10 of 1.2, we're going to apply that power property, multiplied by x plus log base 10 of 5. Okay, there we go. And then b, we're going to do the exact same thing. Okay, I was like, wait a second, these output values are not forming a constant ratio. Okay, but we do have where the log of f is forming an arithmetic sequence, or a linear pattern. I'd like to call it a linear pattern myself. Okay, both x and log base b of y, I guess we can call it y, f of x, whatever, form a linear pattern. That makes it exponential. Okay, I am not totally sure. Let me think about this for a second, how I want to proceed here. All right, so I got a couple of ideas. I think what y'all would be most natural to do is just kind of figure out what is f of x, right? Extend the table, so to speak. So I'm going to say, okay, well, then f of x, I'll do this once in red, and then I'll just kind of like verbally go through the rest of them. So it's going to be a new row of my table. I'll do that in black. But so pretty much log base 2 of f is equal to 2 when x equals 0. That's what this data point right there is telling me. And if I wanted to figure out what the actual value of f was, I need to get rid of the log. And we get rid of the log by taking, a number to both sides power. So I'm going to take 2 to both sides power. 2 to the log base 2 of f of x equals 2 to the 2. So, f of x equals 2. Oh, no, not 2. 2 to the 2, which is 4. All right, so I'm going to have f of x equaling 4, 2 to the 2. This one would be 2 to the 3, because the only thing that would change would be that number. It's the power of x. Or the power of 2, pardon me. 2 to the 3 is 8. 2 to the 4 is 16. 2 to the 5 is 32. And 2 to the 6 is 64. Okay. And then I think I'm just going to proceed as if we had been given the table, exponentially. And look, we're seeing that common ratio. It's doubling each time when the x's are evenly spaced. But I still like this response here. Mostly because it's reasoning with the information that we were given in the statement of the question. Okay, so I've got that f of x is going to be equal to some number a times b to the x, and b is going to equal 2 because that's the multiplier I'm seeing between the output values. I will also point out that it's not a coincidence that that is the same as that 2 right there. So I'm going to use that in the next one where we've got kind of the same style of table when I take a different approach. All right, so 2 to the x, and then I think when x is 0, I need to get 4. So I think it's going to be 4 times 2 to the x. Yeah, I see that. And then you could, kind of check that by just plugging in one of or maybe one of the farther away values. What's f of 3? It's going to equal 4 times 2 to the third. 2 to the third is 8. 4 times 8 is 32. 3 does go with 32. Okay, I feel good. I plugged in some random point and it worked, so I must have good. If you had to be certain, you might plug in all the points to make sure. Okay, but then we're going to want to take the log of both sides. It's said to take the... you look at this, it's got a base, the base of the exponent is 2. You would really want to take the base 2 log of both sides. But if we were graphing, we'd probably take the log base 10 of both sides. Log y equals log of 2 to the x base 10 plus log of 4. I'm going to split over that multiplication first, and then I'm going to deal with the exponent property. So that would be log y, log base 10 of y, equaling log base 10 of 2 times x plus log base 10 of 4. But I think it's, at least to me, it looks like I should probably take the base 2 log of both sides. And so I could probably make that happen. I'll just switch into like green or something and say, all right, log base 2 of y, that's going to equal log base 2 of 2 to the x plus log base 2 of 4. And yeah, you could stop there, but there's some logs here that could be simplified, right? Log base 2 of 2 to the x, what exponent do I put on 2 to get 2 to the x? Just x. So that's going to be log base 2 of y equals x plus what exponent do I put on 2 to get 4? I put the 2 exponent on 2 to get 4, so that's going to be x plus 2. And then I'm just going to point out that we could see that relationship from the original table. And that's kind of hinting at, oh, whoops, I zoomed in too far. Log base 2 of f is 2 bigger than the input value. And that's kind of, I'm going to just go off of that kind of level on the next one, and I'm going to do this in reverse. So you can do it in whatever order you like. You could do what I did in part B and write out the table by figuring out the actual output values. Or we could start here on C by just trying to figure out what is the rule. The y-intercept is going to be 5. So log base 3 of y, that's going to equal something plus 5. How many x's? What's the slope? When I increase x by 1, log base 3 of f decreases by 2. Yes, it's decreasing by 2 every time. And, oh, yeah, I forgot to explain why it's an exponential relationship. I will do that. I'm just going to bring in whatever I said last time, just copy it in. But log base 3 of y is negative 2x, right? Because that's what it seems like the slope is on that linear pattern. So negative 2x plus 5. And if I wanted to do this in reverse to get the exponential equation, I could take 3 to both sides power. So I could say 3 to the power of log base 3y, which is going to be y, is going to equal 3 to the negative 2x plus 5. It's like, wait a second, that didn't exactly look exponential. But if we just keep working, eventually we will be able to show that it's exponential. This is definitely going to be y. We're going to work on this exponent property right here. When we're adding 2 exponents, that's because we multiplied 2 things together with the same base. So this would be 3 to the negative 2x times 3 to the 5. It's like, oh, that's interesting. Yeah, I'm just going to, I'm going to have faith on this, and then I'm going to come back through and do it the other way and show you that it does end up working. 3 to the 5, that I think is 243. Because 3 to the 4 is 81, 243, yeah. Okay, so 243, so this is regular y, is equal to 243 times 3 to the negative 2x. I'll do another exponent property there. 3 to the negative 2, that's 1 over 3 squared, so it's 1/9. And there we get an equation that's very exponential. Also, look at that. I've got exponential decay, and that makes sense because the log of f is decreasing. And that's something we've seen on the semi-log plots just very briefly, that when we see a kind of a negative slope on the linear pattern in the semi-log plot, that is because we've got exponential decay. All right. So if I was going, so I wrote it in terms of all of that. I am going to be grabbing this though, copying it and pasting it, right? Because it's the exact same thing. Both x and log with some base b of y form a linear pattern. All right, now if I was going to do this by extending the table, okay, it's going to be, if I have log base 3 of f equals 5, then f equals 3 to the 5, right? I'm going to take 3 to both sides power, and then I'm going to say f equals 3 to the 5 is 243, not 243.5. All right, so 243, And then, oh, it's just 3 to each power. 3 to the 3 is 27, 3 to the 1 is 3, 3 to the negative 1 is 1/3, and 3 to the negative 3 is going to be 1 over 27. And then what you could do is, yeah, I mean, the 243 is promising because you plug in x equals 0 and that's what you're going to get. I feel good about this result. I'm just going to kind of stop there. Okay, now the function f is graphed on the semi-log plot here. Like I was saying, okay, it's semi-log plot. It looks like a linear pattern with a negative slope. It's got to be exponential decay. And I only see one of these that is hitting that mark, right? I see basically I'm looking at this and I'm thinking exponential decay. Okay, and exponential decay is y equals a times b to the x, where b is between 0 and 1. And so I'm just looking for that. That's only c. There we go. Okay, and then number 6, I think this is the last one. Okay, group of students in Mr. Passwater's class. Okay, so we're going to combine this with the residual plot discussion. I like that. All right, graphed a set of data consisting of the 6 points shown on the semi-log plot there, where the vertical axis is logarithmically scaled. Then they're going to use the data to create an exponential regression model. I think what we're supposed to say here is like, oh, look, if I draw in a line connecting these dots, doesn't look like they're lined up, because I'm definitely going through that point, the point where x equals 2, and I'm going through the point where x equals 5. Okay, so I think this data should be approximately exponential, not exactly. So I'm not expecting all zeros in my residuals. But this does look like a good model because the data are showing a linear pattern. So an exponential model is good. Okay. I think I'm going to actually even write that. And I know that based on what I'm seeing from the semi-log plot, the linear pattern. All right, so if it's a good model, then we should see no pattern in the residual plots. And of course, this being a trig class, I think it's very easy to be like, oh, I see a pattern there. But of all of these, it has the least pattern, is what I would say. And so I'm going to say that no pattern, that means it's a good model. There we go. That's it. And that's all for this problem set. So that'll be all for this video. Thanks for watching.